Right, for these, we're determining the limit at infinity for each function. And just like before in the notes, sometimes we'll need to take a limit from both sides because there may be two horizontal asymptotes, or it may be a situation where we have an oblique asymptote. So the limit as going to positive infinity may be different than the limit going to negative infinity. But then in some instances, we'll just have to do it once. So we'll be able to analyze that given the situation, and I'll kind of help you through that. So we are in this one, we have, this is similar to, I think, the last example. We need to multiply these two binomials to be able to multiply out this binomial to really be able to analyze better what's going on here. So I'm going to start with the limit going to positive infinity. I have 6x squared subtract 12x plus 2x subtract 4 all over 4x squared negative 28x plus 49. So remember, I only care about my leading coefficients, so all of this doesn't even matter. So I'm just looking at 6x squared to 4x squared. And what happens here is because I have these two x squared, since they're matching, this is just going to equal 6 over 4 or 3 halves. And because these cancel out and they're the same degree, my only horizontal asymptote would be y equal to 3 halves. Because even if I were to put a negative infinity into here, it would force them both to be positive, and they're increasing at the same rate because they're both squared. So my only horizontal asymptote would be y equal to 3 halves. If I'm just examining the limit, we're going to get 3 halves as it goes to positive infinity and negative infinity. All right. For our next one, it is a similar process. So I'm going to go ahead and multiply out again. We have the limit as x goes to positive infinity of, what do we have, 4x subtract 12x squared plus 10 subtract 30x over 9x squared subtract 12x plus 4. So again, we only care about these leading coefficients. So I'm going to rewrite this as the limit as x goes to positive infinity of negative 12x squared over 9x squared. And again, because these are both squared terms and because they're going to cancel out since they're increasing at the same rate, it doesn't matter if I'm putting a negative infinity in or a positive infinity, the output of this is still going to be negative 12 over 9, which simplifies 3 goes into both of these to negative 4/3. So the limit is negative 4/3. If we were asked about the horizontal asymptote, we would get y equal to negative 4/3 as our horizontal asymptote. All right, in this last one, notice we're going to have a cubic term now, so things are going to be a little bit different. So I'm going to take the limit as x goes to positive infinity. I have 5x cubed plus 20x subtract x squared subtract 4 all over 25x squared plus 10x plus 1. And my leading coefficients here are this 5x cubed and this 25x squared. So I have the limit as x goes to infinity. I'm going to simplify this down. 1x cubed over 5x squared. And now I can simplify this down even further to simply 1/5 x. Well, when x goes to positive infinity, this is going to equal positive infinity. However, when x goes to negative infinity, hold on. When x goes to negative infinity, I'll put this up here, of 1/5 x, because it's going to simplify down the same way. This one will go to negative infinity. So this is most likely an oblique asymptote. It is an oblique asymptote. So we would have some type of linear function And as my function's going to negative infinity, my y's will also be going down to negative infinity. And as I'm going to positive infinity, they'll be going to positive infinity. All right. Let's take a look at these square root functions and then move on to the next section. All right, so our next one is number 4, which is the limit as x goes to infinity of the square root of 25x to the 4th plus 2x all over x squared. So just as a reminder, we're only looking at those leading coefficients. So I'm going to cancel this out. And again, the only reason we can do that is because x is going to infinity. If x is going to a constant value like 5, 7, any numerical value that is not infinity, we cannot just like arbitrarily cancel out terms. This only happens because infinity, because this term is so much larger if it's x to the 4th than 2x. So now I have the limit as x goes to positive infinity of the square root of 25x to the 4th over x squared. I'm going to take the square root of 25x to the 4th, and I'm going to put absolute value sides around it. So I have 5x squared all over x squared. Well, notice this term has to be positive. This term actually has to be positive, so we don't really need these absolute value symbols in here because I'm still going to get a positive result out regardless. But again, I just like to put them to be safe. And it's going to go to positive infinity. So this is going to equal positive infinity. Oh, no, I'm sorry. They're increasing at the same rate. So this is going to go to a positive 5. Because this increases at the same rate that this increases, so they cancel out, and we're just left with this positive 5. If we look at this from the left as well, the limit as x approaches negative infinity would also yield a positive 5. So the only horizontal asymptote I have here is y equal to 5. All right, in our next example, we have the limit as x approaches infinity of the square root of 7x to the 6th plus 3x squared plus x all over x cubed plus 4x squared. So again, gone. I'm going to rewrite this. I'm going to take the square root. Square root of 7, that's not a perfect square, so it's just going to be the square root of 7. This is where those absolute value signs really come into play. I need the absolute value of x cubed. So remember, the square root of x to the 6th is x cubed. You have whatever's there, because what we have here, if we're looking at rational functions, is I have 7 to the 1/2 and x to the 6th to the 1/2. And remember, our power rule from exponents says that you multiply these two. So half of 6 is 3 all over x cubed. So when I put in positive infinity, it's no big deal, right? I still get the square root of 7 out. But let's see what happens when I put in negative infinity at this step. I have the square root of 7 over absolute value of x cubed over x cubed. So if I put negative infinity into my denominator, I'm going to get a negative out. If I put negative infinity into my numerator, this is forcing this to be positive because, again, we can't get a negative result out by taking the square root of this function. It's just not possible. So I get a positive out. A positive divided by a negative is a negative root 7. So this function actually has two horizontal asymptotes. It has a horizontal asymptote at y equals root 7, and it also has a horizontal asymptote at y equals negative root 7. All right, let's look at our last two. We have for number 6, we have the limit as x approaches positive infinity of the square root of 9x to the 8th, subtract, it doesn't matter, 2x cubed, subtract 6x, all over 2x to the 4th, subtract 10x, and that's all plus 3. Well, I can break these up using addition. So I'm going to do the limit as x approaches infinity, and I'm going to notice that this all goes away and this all goes away. So I have the square root of 9x to the 8th all over 2x to the 4th plus the limit as x goes to infinity of 3. Well, the limit as x goes to infinity for 3 is just 3 because this is my constant rule. I need to work this one out a little bit more. So let's go ahead and check out what's going on. We have the limit as x goes to infinity. If I take the square root of 9, I get 3. The square root of x to the 8th is x to the 4th. Again, you just half whatever that exponent is. It's positive, so I don't technically need those absolute value signs, all over 2x to the 4th. Well, these are getting large at the same rate, so I can cancel those out, and it's just those coefficients that is going to result in. So I have 3 halves plus 3, which is the same as 9 halves, so I end with 12 halves. Oh, I'm multiplying by 2, that's why. I'm ending with 9 halves, because this would be 6 halves, which would yield 4 1/2. So you may have gotten 9 halves, or you may have gotten 4 1/2. Coming from the left side, it would be the exact same thing. So the only horizontal asymptote in this situation would be y equals to 4 1/2 or 4.5 or 9 halves, whatever you prefer. All right, for our last one, we have the limit as x approaches infinity for 3x divided by the square root of 9x squared, subtract 1. I'm not going to simplify anything in the numerator. You can't get rid of anything yet because that is, it doesn't have a square root, right? So we're just going to keep that way. In my denominator, I'm going to say, well, that's negligible. It doesn't even matter. The square root of 9x squared is going to be 3 absolute value of x. And so these we're going to cancel out. And as because they're getting larger at the exact same rate. And so I'm left with 3 over 3 or 1. Because I have this absolute value of an odd exponent, I am going to go ahead and take the limit as x approaches negative infinity. Because I can see that if I sum at negative infinity, I'm not going to get the same answer out. So I have 3x over 3 times the absolute value of x. If I put negative infinity in here, I'm going to get a positive value. If I put negative infinity in here, I'm going to get a negative. This is going to yield a negative 1. So this function would have 2 horizontal asymptotes, one at 1 and one at negative 1.